Well, welcome back, everybody. Now, I should be joined by my co-host for today, Carrie. Carrie, are you on the line? Hello, Carrie.
I am indeed. Hello.
How are you doing this morning? Although it's lunchtime in the Netherlands where you are, of course.
Yes, indeed.
Yeah. So, Carrie, you will be hosting this track with me. What's our track again?
We are track 1. We are the DevSecOps track. There's some really great talks today that I'm really excited to get to listen to from the seat.
That's a nice part of being a track host. So we will get back to our track topics later. So that's Carrie. Reach out to her if you need her for anything. Reach out to me. In the meantime, without any further ado or messing around, it's with great pleasure, wonderful pleasure, that we get to welcome Liz Rice from Insolvent to the stage. Liz is a tower of strength in the community, a legend actually in what we do. And today she's going to be kicking off the conference with her keynote, how eBPF is setting the world alight. Liz, welcome. Yay!
Thank you very much, Jamie. Thank you to everyone here at WTF is SRE. I've been to a few virtual events put on by this team, and they're always really fun and really good events. So I'm really excited about this. I hope you can see my fake flames here. I really like this fire theme. And I've tried to embrace that with my my talk this morning about how eBPF is setting the world alight. So I'm the Chief Open Source Officer at a company called Observability. You may also have come across me in my role as the chair of the CNCF's Technical Oversight Committee. Now, I joined Observability pretty recently. I've only been there for a couple of months. And the reason why I joined is because I've been very excited about eBPF and the really powerful things that eBPF can enable, particularly in the world of cloud native. And Observability is packed full of eBPF experts, people who are not just maintaining the Cilium networking stack, which I will touch on later, but also folks who are actually maintaining eBPF within the Linux kernel itself. So I'm really fortunate to have lots of expertise kind of on tap, and I'm learning a lot about eBPF. So let me just try and share some of that knowledge with you this morning. So traditionally, when we want to explain something, I can hear a bit of background noise. I'll just mention that. Okay, sorry, yes. So I'm going to explain what eBPF is, but more importantly, why, particularly if you're an SRE, I think this is going to be of interest. I think you're going to see more and more eBPF-based tooling in your lives today and in the near future. So traditionally, when we're talking about something and it's got an acronym name, we say what that acronym stands for. In this case, eBPF stands for Extended Berkeley Packet Filter. I could spend some time talking about the history of why it's called that and where that came from. I actually don't think that's terribly helpful. I think it's more important to talk about what eBPF actually does in practice. What it really is the ability to make the kernel programmable. So you can write custom code and have it run in the kernel without having to load a whole new kernel module. You can load these eBPF programs into the kernel dynamically as and when you need them. So you probably know that we usually write applications in user space. So eBPF enabled programs are no different. They have a user space part, but that user space part can load eBPF code into the kernel. These eBPF programs get triggered by some kind of event that happens somewhere in the system. There are lots of different types of events that we can attach eBPF programs to. It could be a network packet arrives, or some application calls a system call. It could be that the kernel hits a particular trace point or calls a particular function. A whole realm of different events that we can hook our eBPF programs to. And when that event happens, our eBPF custom code gets run. So I have a very simple example of an eBPF program that is going to write out a message to the screen every time execve gets called, execve being a system call. So this is my eBPF code. I'm going to just change it so that you can see that it's kind of live. I'll rebuild it. And when my eBPF code, which is written in C, when it gets called, it's basically just going to print out a trace line saying, hello. This is the hello world of eBPF. And I also have, so this is the part that's going to run in the kernel. And I also have a user space part that basically loads that executable code, well, reads it from a file, loads it into the kernel, and then attaches it to some event. The event in this case is called a kprobe, and I've associated it with starting the system call execve. Now, execve is what runs a new program. So every time you run something new, a process gets created, and then this system call execve gets called to actually execute it. You don't normally see this. You're not normally interested at the system call level, but it's certainly quite interesting for an eBPF program. So if I make my program and then run it, I have to run as root because you do need privileges to load eBPF programs. That makes sense. You don't want people running just anything in the kernel without permissions. Okay. So as things happen on this virtual machine, and there is quite a lot happening because I'm remotely logged into my virtual machine through VS Code, we can see my message getting traced out. We can see information about the process that's triggering those calls. And if in this window over here, I also run something, and that was this bash process. If I run PS, we should see another process. We can see 29947. So if I scroll down here, I should eventually see, yeah, there's my the event being triggered by me running a new process in inside bash. Now, that's kind of not a particularly useful program. It's just hello world. There is a sort of slightly more advanced version of that in my GitHub site. So if you want to look into that code, expand on it, maybe try out some more examples, I do have that GitHub. But what I really want you to hold in your head is that every time a system call got triggered, regardless of what process made that system call, my eBPF code got triggered. So my eBPF code could see everything that's happening across that virtual machine, regardless of what process triggered it. So that's really going to be essential to why eBPF is so powerful. And let's have a think about what that means if we're running applications in Kubernetes. So in Kubernetes, we're running our applications inside containers, and those containers are running inside abstractions that we call pods. Regardless of how many containers there are and how many pods there is just one kernel per host, per virtual machine, or if you're running on bare metal, it's per physical machine, one kernel per host. So that kernel is being shared by all the processes and all the containers that run on that host. Now, whenever an application inside a pod wants to do something, it has to ask the kernel for help. User space applications can't make networking requests or access files or kind of do anything really very interesting without assistance from the kernel. The kernel is going to get involved every time you want to read or write from a file or send a network request. In user space, pretty much all you can do without kernel assistance is a bit of basic adding up. So the kernel is aware of pretty much all the interesting things that are happening on the systems. If you want to create a new container on a host, the kernel is going to be involved to create namespaces and create C groups and create these abstractions that we call containers. The kernel sees everything. Everything that's happening across all of our applications that are running in user space, there are data structures associated with that maintained within the kernel. So if we write eBPF programs and attach them to the right events in the kernel, they can be aware of all of the interesting things that are happening across this whole node. We can write user space code that communicates with these eBPF programs running in the kernel, and we can bring all this information together in really useful ways. We can use this information for observability and security and networking. When it comes to network packets, we can not just redirect packets, we can drop them, so we can use them for things like network policy, all running in eBPF. So for my next demo, I wanted to just show you quickly how Cilium network flows are Kubernetes aware, to give this example of how eBPF can be aware of these Kubernetes constructs. So I have a 2-node Kubernetes cluster here, and I'm running Cilium on it. So Cilium is the networking enabler on this cluster. And you can see there is a daemon set here. This is the main part of Cilium, running one instance per node to provide connectivity to all of the endpoints, all of the pods and hosts and external world that we're interested in. And if KS is my short for kube control in the kube system namespace. And if I get the pods, I can see there are 2 Cilium pods, 1 per node. That's what we expect. So let's exec into one of these. It's not what I meant. So I run a shell inside one of these Cilium agents, and I can look at the state of endpoints that this particular agent is aware of. So this is the Kubernetes endpoints that the agent on this node is aware of. And you can see that we've got Kubernetes information like the namespace for the pod, labels that might be identifying different applications. And these are associated with IP addresses. So by keeping track of what pods are running, by querying Kubernetes and tying that up with the networking that we're enabling, we can tie Kubernetes identities, Kubernetes information to network traffic. So if I were to look at Hubble, to look at the network flows that this node is aware of, we can see that they're not just talking about IP addresses and ports, but they're also talking about pods. And we're able to see quite a lot of detail about the messages that are flowing and which services and which pods they're flowing to and from. And if this is a screenshot of the Cilium's Hubble UI, which I nearly demonstrated live, but managing the windows turned out to be the most complicated thing about it. So I took a screenshot. But you can see that by being aware of the traffic that's flowing through the cluster and that Kubernetes information, by pulling it together, we can get this really powerful view of what's happening in the cluster. This is a really good example of eBPF-powered observability. So eBPF apps have this view across the entire node. It allows us to tie our tooling into knowledge of Kubernetes applications. It also allows us to be really efficient. One of the things that we can do by writing custom code in the kernel is that we can potentially replace some parts of the kernel if that makes sense for a particular application. And I want to show how by using eBPF, we can make networking really high performance in a Kubernetes environment. So typically, container networking on a traditional host looks something like this. So the pod is created with its own network namespace. And that means it has its own networking stack running inside that network namespace. So all of those boxes there that talk about IP tables and Linux routing, that is the network stack running inside that namespace owned by the pod. And the pod's networking namespace is connected through this virtual Ethernet pair to a networking stack on the host. And because of the network namespaces, those two networking stacks are not aware of each other. For all intents and purposes, the networking stacks think that they're running on entirely different machines. That's kind of the point of isolation. But what it means is if a packet arrives at the Ethernet port for the machine, it has to go through the IP stack on the host. Then it gets to the virtual Ethernet pair for the pod, goes through another networking stack in the pod. With eBPF, because we're aware of not just the networking on the host, but also the networking inside the pods, we can replace a lot of this host networking stack with a more straightforward implementation in eBPF. Just by the number of boxes, you can tell this must be higher performance, right? Now, this doesn't happen for free. This isn't like an eBPF flag that you turn on. This requires writing the equivalent code to handle networking in eBPF code that is attached to events in the kernel. We actually get to hook eBPF code into an event that's triggered as close as possible to when that network packet arrives at the physical network path. This is called XDP, or Express Data Path. So we can get hold of these network packets really early on in their life cycle as they arrive at the machine. And then because we have awareness of the pods and how they map to IP addresses, we can take that packet and send it straight to the pod's virtual Ethernet interface, where it then just goes into the pod's networking stack as normal. So from the pod's point of view, this just looks like nothing has changed, but it is a lot more efficient. And one of the reasons why I wanted to show this is because I can fit with today's theme and show a flame graph. So in this flame graph, we can see what's happening, like how much, what functions we're spending CPU time in as a packet arrives on a host and then gets sent into the appropriate pod. So you can see the packet, or there is some CPU time spent processing the packet in some eBPF code. And then it spends some time, it gets switched into the context of the pod. It spends some time in the TCP/IP stack associated with that namespace, and then it goes into the socket. You can kind of see, I think, that the eBPF code looks like it's taking less time than the TCP/IP stack does. That certainly bears out when we look at performance. We've recently done a lot of performance benchmarking tests, and you can find a lot of results on the Cilium blog. But the main takeaway is that using eBPF-based networking solutions, we can do container networking nearly as fast as we could just do host-to-host networking. In this graph, we're looking at the throughput of round-trip request response messages. The blue bar is what happens if we're not running containers at all. We're just running sender and receiver on two different nodes. So that's kind of the highest possible throughput. The red and orange bars are using eBPF-enabled networking stacks. And you can see they're approaching the maximum speed. They're approaching that node-to-node baseline. The yellow and green stacks are networking with eBPF not enabled. So you can see how without that eBPF optimization, the throughput is significantly lower. eBPF is really enabling much more efficient networking. So we've talked about how eBPF apps have this view across the entire node. And one really important aspect of this is that we didn't need to change anything about the user space application or the way it's configured to get this view. For our eBPF programs to be able to inspect what's happening, they're running in their kernel, so the application doesn't need to know anything about it. Nathan Leclerc came up with this really great bumper sticker. My other sidecar is a kernel. And I think we're going to see more and more how eBPF can replace the sidecar model for a lot of observability and security tooling. So let me explain that a little bit further. In a sidecar model, we have some number of application containers in a pod, and we also have a sidecar container. And maybe that sidecar is running logging, tracing, security, some kind of additional functionality that we want to inject into all our applications. And in order to have that sidecar container run in the pod, it has to be defined in the YAML that defines that pod. You might do that manually. It might be injected through some kind of scripting. It might even be done through an admission control webhook, but something has to mess with the configuration and change the YAML to add that sidecar. So there is the possibility that that might go wrong. Somehow that might not be correctly injected. If your YAML doesn't end up with the sidecar injected correctly, the sidecar is not present and it just can't observe that pod. If we're using a sidecar model, we have to have a container running inside the pod so that it's sharing namespaces with those user applications. We don't need that if we're using eBPF because we can see everything that's happening from the perspective of the kernel. So I think we're going to see not just the efficiency of eBPF, but the fact that it's easier to instrument because we don't need to make any changes to applications or their configuration. This is a really powerful benefit of eBPF-based tools. Which leads me on to talking about some of the tools that you can use today. So I've already talked a fair bit about Cilium, which is a networking plugin and so much more. It's providing a lot of network observability and security. There are also several other prominent tools in the cloud native ecosystem that I wanted to mention. Falco is a CNCF project, and it's a security project that can alert you when eBPF code detects malicious or suspicious events. Again, it's because it's running in the kernel, it can observe these events across the entire node. Tracy is another eBPF-based security app from my former colleagues at Aqua Security, and it's pretty similar to Falco, perhaps a lighter weight approach, and it allows you to define the security events that you're interested in using Rego, which is the language that Open Policy Agent uses. And the last tool that I wanted to mention is Pixie, new kid on the block. Lots of excitement about Pixie. It just got open sourced and they've applied to make it part of the CNCF as an eBPF-based observability tool. So there's a lot of existing tooling out there that you can already experiment with and potentially use in production today. So we've talked about how eBPF applications can see everything across the whole node. You saw in my Hello World example how the eBPF code can be aware of the process where an event happened. And you saw in Cilium how network flows can be associated with Kubernetes identities. What if we bring those two things together? So this is a screenshot from something we've recently been working on that does exactly this, brings together the process awareness and the networking awareness and the Kubernetes awareness. So you can see here that within a pod called crawler something, some processes are running, and this node process running node server.js made two network connections, talking to the Twitter API and talking to Elasticsearch. So we've got visibility here into exactly which process running inside which pod created which network connections. So imagine if one of those connections were to a suspicious endpoint, like a cryptocurrency mining IP address. You'd have all the data to figure out what had created that network connection. You could be notified when these malicious events happen. You could use this evidence to track down how that malicious activity had happened in the first place. Was it built into the container image that you were running, or did your container get compromised? You'd have a lot of clues at your fingertips. And that would all be thanks to the power of eBPF. This is why I think eBPF is the future of observability and security tooling, as well as networking performance. And it's not just for Linux. Just recently, Microsoft have announced that they are working on eBPF for Windows. It can't be exactly the same because the data structures that you have in the Linux kernel are not the same as the data structures in the Windows kernel, but the concepts are going to be similar. There's a lot of focus within the community on trying to make things as reusable as possible and use some of the existing eBPF tooling so that it can be used in the Windows world as well. I think this just goes to show we are really a long way from the end of the journey with eBPF, where there's so many things that we're going to be seeing come out of this technology. I want to emphasize that it's not just a checkbox. You can't just turn on eBPF. You have to write specialist eBPF code to take advantage of these capabilities. But the future is wide open for some really exciting innovation in this space. If you want to learn more about eBPF, there's a community site at ebpf.io. Cilium also has a cilium.io site, and we have a Slack channel, slack.cilium.io, where we are more than happy to talk to people about eBPF and Cilium more generally. That's me done. I haven't figured out yet how, if there's some kind of Q&A functionality. So hopefully Jamie will tell me how that's going to work, if that is going to work, or Carrie will. And I think that is it from me. So thank you very much. I hope that's made you excited about eBPF.
Yeah, very much so. Thank you so much.
Thank you.
It's been really exciting. Jamie, you're on mute. Just a reminder.
Thank you. How was my sound, by the way? Because I was getting feedback that my mic was weird.
Sounds good to me now.
Sounds good to you. Okay, yeah. It's weird because it sounded good on the AV. Anyway, enough about that. Now, the good question is there Q&A facilities? Yes, there is, Liz, and it's been very busy. Carrie, do you have access to the questions?
Yes, so I've been monitoring the chat for all the questions, and some that have stood out. Someone asked, is there a way to export log details of block packets to an external system like Elastic or Splunk?
Yes, absolutely. Certainly in Cilium, that is. Now, I can't remember off the top of my head if that's part of the open source functionality or if that's part of enterprise, but certainly the general capability of exporting logs, absolutely. Yeah.
Great.
And it's a very widely used use case. You want to throw all that data into a SIM somewhere and then be able to analyze it later.
Nice.
Very cool. We do have another one about IP tables. Why is eBPF? I still can't say it, Liz. eBPF. Why is eBPF faster than IP tables?
It's a really good question. I think it comes down to IP tables being, or the whole TCP/IP stack being capable of doing all of these different network functions. It's, you're going through all these different components within the kernel to check whether there's like NAT translation or forwarding rules or the mangling thing that I'm a little bit hazy on, to be honest, exactly what happens with mangling, but there are all these different steps and you don't necessarily need them if you already just have a map of, well, I know this IP address, the endpoint for this is this virtual Ethernet interface over here. So we can just do a very straightforward mapping because we've set up that network connection in the first place. Those IP tables are general purpose networking capabilities that we don't always need for our container networking.
Nice, thank you. And then there's one more question that came in that I'm actually also curious about. Is there a use case for eBPF with service meshes?
That is a really great question. And the fact that you don't need sidecars, I think, does point in that direction. So there's actually already quite a lot of the capabilities that you would look for in a service mesh that you can do with Cilium today. One example, and it's not exactly a like for like, but I do think it's really interesting. So one of the reasons people use service mesh is for encrypting traffic between services. So you can use a service mesh to set up mutual TLS. And that's at the application level of networking. With a networking stack, you can turn on encryption lower down in the stack with things like IPsec and WireGuard. The application doesn't need to be aware. You don't need a proxy or a sidecar that's terminating those endpoints for you because it's handled for you at a networking layer. So you can get encryption of your traffic by implementing it in the network layer. That's just one example of something that you would do in a service mesh, and that you maybe could choose to do that at the networking layer instead. There's lots of other capabilities that service meshes give you. Some of the things like redirecting traffic from, maybe for like canary deployments. So you're going to direct a certain percentage of traffic. Absolutely, that is the kind of thing that could be implemented in eBPF for sure.